Okay, so this was the diagram where we did our last lecture, and I would like to erase it now. Before we were supposed to talk about melting, but before that I think I should tell you a little bit more so that you don't have any confusion later on about crystallization. We do it for 5-7 minutes and then we will move over to melting. Let me erase this. And we are talking about crystallization. We continue our discussion with crystallization bit. Just to clarify a few confusions that you might have in your mind. I drew the diagram again, though the diagram is familiar to you. And so this is A, B, temperature of melting of B, temperature of melting of A, and you can have a diagram like this. I have changed the diagram a bit so that you don't think so. So that's the diagram. This is the temperature axis. XA, or weight percent A, increases from this side to this side. It's 1.0, and so XB in that case is 1.0. And this is a liquid, and this is A plus liquid, this is B plus liquid, and this is A plus B, meaning A solid, B solid. This is A solid plus liquid, B solid plus liquid. And remember from the former discussions, A is pure and B is pure. So below this temperature, this is XE, composition of the eutectic, and this is TE, the composition of the temperature of the eutectic. Now, let's say we take a melt composition right above this eutectic. Right above this eutectic. Let's say we take a composition L0. Now you must, if you look at this, this will be around 50, so this will be around A60 and B40, possibly B40 and A60. This would be the composition of the eutectic. So this will be the composition of the eutectic. Or you can say A is 0.6 and B is 0.4 if you want. Or you can say A60, B40 as the eutectic composition. This is the eutectic composition for the system AB. Now, interesting here. As I was telling you yesterday, the composition of the liquid is A60, B40. Remember from our earlier discussion, this is A component in the melt, and this is B component in the melt. And the melt is a solution or a chemical compound, a polymeric liquid, where A and B are in the proportion of 60-40. But A and B you cannot co-separate. You cannot separate out. So it's like a liquid solution rather than a mechanical mixture. And here you have, here at this point, here you have A 0.6 and B 0.4, or A60, B40. This is the composition A60, B40. Now, if you cool the liquid now, the liquid coordinates move along this line till you reach the position, say L1. Now at L1, what is the composition of the solid? That's the composition of the solid. What is the temperature at which crystallization starts? the temperature where the crystallization starts is temperature of the eutectic. This is the temperature at which crystallization starts. Why? Because now the melt composition has reached a point, this point, where liquid A and B are in equilibrium. So if it is so, then A and B has to precipitate out. How will it precipitate? How will it precipitate? Now you see. The melt has A and B components in the proportion 60:40. So it crystallizes A solid and B solid, each of them pure, in the same proportion. So what happens? The solid that you form has A60 mineral and B60 mineral, both are pure. So what is happening in the melt? The melt has a ratio of 60:40. It is crystallizing mineral A and mineral B in the proportion 60:40. So, because you keep the ratio same, the mineral composition cannot change. But the proportion of the melt will decrease and more A and B precipitate out in the same proportion as in the eutectic. And this I can't show. So this is a situation where your liquid composition and solid composition coincide. The liquid composition and the solid composition coincide. But the proportion of the solid comprising of A60, B40 and the liquid having the composition A60, B40 in terms of components, they're one and the same. And this is how crystallization will continue till the last melt is exhausted and the last solid that is produced is A60, B40. Is A60, B40. So from the beginning, the liquid composition does not change, the solid composition does not change, but the proportion of the liquid decreases and the solid increases. But this cannot be shown in the phase diagram. This cannot be shown in the phase diagram. But this is the only point in the diagram where the solid composition will have the same composition as the liquid all through its crystallization. The solid forming of A and B crystals will have the same composition as that of the liquid in terms of components A and B. So, if now we can just a little progress a bit more from here, so we can divide this diagram into essentially three parts. Part 1, Part 2 and Part 3. Here on this side you will first have precipitation of B and then co-precipitation of AB. On this side you will start with the precipitation of A and continue with co-precipitation of B. At the point number 3 you will always have AB in the proportion of the eutectic. So there are three parts to the diagram. If you are here, you will start with crystals of A, then it will be joined by AB when the melt reaches the eutectic. Here, you will start with crystallization of A in this part, and then when the melt reaches the eutectic, you will have AB added to the solid. But in 3, which is the dividing line, you will have always, from the beginning till the end, AB precipitating in the same proportion through the crystallization history. Both the composition of the solid and the composition of the melt in terms of A and B component remains unchanged. Right now? So, I hope I have done the clarifications, there is a book. I will just 1 second. Yeah. For those who are interested, you can refer to this book here, An Introduction to Igneous and Metamorphic Petrology by John Winter. Now, for the discussions that we will have for considerable classes now, I will follow this book for you. I will follow this book. And these diagrams, phase diagrams, are very well discussed here. But, I'm giving you a little more details into it, because in a book, if you have to write so much and clarify each and every point, that book will become as big as a mountain and difficult to open. So it's important what I am saying to you. You please understand it, and this will make your reading much easier, because I have taught it beyond what the book says. Crystallization. But now we go into the topic of melting. That's not covered in the book. It's not covered in almost all books. So you be very careful, and I will try to be slow a little bit. Just remember one thing before I start. Melting, or equilibrium melting, which I will call equilibrium melting, this is the reverse of crystallization process. So in a crystallization, the process that you went through till the end, in melting, the end is the beginning. The end comes first, right? So I will talk about melting, and you please be very concentrated on this, because you won't get the help either in the internet or most of the books, or almost all of the books. You will not get this, and it's very important for us to understand how things work. Yeah. In melting, you start with a rock. You start with a rock. And rock is a mixture of minerals. Is an aggregate or a mixture of minerals. So here, this is XeAb, and this is TeAb. I don't need to explain this you take it for. Let's take, let me take this as 0.25, 0.5, 0.75. Let's take these values as this. And let's take a rock, R0. Let's take a rock, R0, which has A60, say B40. Now, firstly, it's a rock. So A is a mineral, B is a mineral, and it's a pure mineral. Remember the equation. A is a mineral, B is a mineral. Where does this composition lie? Let's say A60, A60 would be somewhere here. let's say this is A60, obviously this is B40, and this is your R0. So we have a rock whose composition is here, and we are talking of equilibrium crystallization, equilibrium melting. Now I will draw this line, I will give it a dotted line. We are starting with the rock A60 B40. Now what happens? A rock normally is at the surface, let's say a rock at the surface temperature. Somehow we melt the rock. We increase the temperature of the rock. So when will the rock melt? If a rock comprises of pure A60 and B40 pure, at what temperature will the rock melt? The answer to this is the temperature will melt when we have reached the temperature TE. That is where temperature, that is where melting will occur. When we reach temperature eutectic, melting will occur. So, if we take this line now, we reach this point. Because temperature line and this line, the intersection of this is the point where melting will start. Now, the next question that is asked, what will be the temperature, what will be the composition of the first melt? First melt, initial melt, what will be the composition? So, before that, we have A and B. When melting is initiated at the temperature of the eutectic, what is the composition of the melt? Composition of the melt. Reverse of equilibrium crystallization. The first melt will have a composition of this. This will be my first L1. Remember, this is R0. So if we melt L1, the first melt will be L1. That means L1 means what? The composition of L1 is A50, B50. Right? Now, at the eutectic, A, B, and the liquid are in equilibrium. So we know the composition of the liquid is L1, A50, B50. We also know the composition of A and B. Composition of A and B. What is the composition of A? A100. What is the composition of B? B100. So we know the compositions of A and B. And we know the composition of the liquid. This initially was a composition A60, B40. Now when we melt, A60, B40 is A50, the composition that is A50, B50 will be extracted. That means A, B in ratio 50-50. A mineral and B mineral in the ratio 50-50 will melt in a rock where A60 and B40 occurs. So what will happen? If you melt A50 and B50 in a rock which has A60 and B40, obviously the rock composition should move in the direction of A. So what will happen? What will be the composition of the solid? Mark my words. What will be the composition of the solid in equilibrium with L1? Composition of the solid. We know that it contains pure A and pure B. But in what proportion now? In what proportion now? We also know the solid will move in this direction. But what will be the composition? What will be the proportion of A and B that will define the solid S1 in equilibrium with L1? Have you understood? So now, it is something like this. This is our L1. This is R0. I'm drawing this line here. And this is the line. This is the first melt L1 that it produced, or at the eutectic. And this is our initial R0. Now, I am asking, my question, fundamental question is, where is S1 in equilibrium with L1? Where is S1 in equilibrium with L1? We know that it comprises of pure A and pure B. But where do I plot the point S1? Have you understood? Let's say this point is plotted. It's not right. Let's say this point is plotted. And say this point. This is, let's say, this is my S1. And I don't know it, but I'm just drawing it. See here. R0 will lie between L1 and S1. That's very logical. Because the two of them will mix. Now, this is M and this is N. What is M? M, you see, is S1 R0 divided by S1 L1. What will be this? M is the fraction of liquid. And N is the fraction of solid. It's Liver's rule. See again. If I take R0 and melt it, the first liquid will be of eutectic compositions. This liquid will be A50, B50 in composition. But we are trying to find out where will S1 be. S1 be. And I know here that this is M and this is N. So the fraction of liquid is equal to M divided by M plus N. This is the fraction of liquid. And what is the fraction of solid? N divided by M plus N. Now let's say I have melted 10%. 10%. So M now becomes 0.1. That means N is equal to 0.9. Yes or no? If I say fraction of melt is 0.1, that means fraction of solid is 0.9. So, if this is equal to you see N, fraction of solid is 0.9, then I will have a point here somewhere where this will be my S1, where this is 0.1 and this is 0.9. Tell me, have you understood this? I am looking to plot the point S1. I know it is made up of A and B, but I don't know in what proportion A and B, weight proportion, does it occur. And I want to find that out. So I ask myself the first question, okay, what is the fraction of melt? I can see the fraction of melt is 0.1. So what's the fraction of solid? 0.9. So if this is fraction of solid, 0.9, then I can add 0.1 here, this length, and I can say, okay, so this is my S1. Forget this slide. this is my N and this is N. Have you understood? I give you a little time to think about it. I am going back now. I have a rock. I have melted it. I know definitely that the liquid composition will be A50B50. But I also know the position of R0, A60B40. And I want to find out where will be my S1. But I know S1 contains pure A and pure B in some ratio. Pure A and pure B in some ratio. I want to find out where will I plot my S1. So then I say, okay, what is the fraction of melt? The fraction of melt, say 0.1. I could have taken 0.05. That means 0.05. 0.05. Have you understood? Or I could have taken 0.01. And the rest would have been a fraction of solid. So this would be at this length, would be adjusted depending upon what is the fraction of melt. So depending upon that, once I get this length, this is 0.9 and this is 0.1, and so that means this is 10% melting, and so my point position S1 should be here. There's no way off. Okay? So now what I think is, so you have L1, R0, so now your S1 is here. And this is the composition of your S1 in terms of A and B. This one in terms of A and B. If you keep the temperature and the melting proceeds, L2 will be in the same position, but your S1 will move to the point S2. But the liquid L2 will be in the same position. The composition of the melt will not change, because so long you have A and B minerals, your liquid composition will not be able to leave the detector. And all the while, your solid is becoming richer and richer in A. Because your rock contains A60B40 and your eutectic melt is A50B50. So essentially, your rock will become richer and richer in A. And the melt composition will remain the same till you reach this point where, say, it is S3 and this is L3. Now you say, if it is S3, imagine just before reaching S3, we are there, just one little movement. Before that, A and B should be in equilibrium with the liquid, because the liquid has to be a deuteric. But the moment you reach here, B is 0. The proportion of B becomes 0. Have you understood? When will it become 0? Now you see here. When will become 0 here? Now you see. This is M, this is M. So here, M divided by M plus N is the fraction of melt. Do you understand? M divided by M plus N is the fraction of melt. So, from this length divided by the total length, that means S3L1 or S3L2 or S3L3, you can find out what is the value of M and what is the value of N. At that fraction of melt, B has been exhausted out of the system. B has been exhausted out of the system. So the melt now cannot remain at the eutectic. It has to go this way, because this is where A and liquid are in equilibrium. Only there the melt no more can stay at the eutectic. The melt will only stay at the eutectic when both A and B are in equilibrium with it. So the moment B is exhausted, the liquid will move in this direction. And therefore, immediately you will have S4. Now you will only have A, pure A, in equilibrium with the melt. And this here, M, and this here, N. You can see the amount of M remains the same, but the N becomes smaller. So the fraction of melt increases. This M remains the same and the N decreases. So the fraction of melt decreases. Fraction of melt increases. So more A will go into the melt. More A will go into the melt. As more A goes into the melt, now this is N and this is M. Say this is S3 and this is this is S5 and this is L5 in equilibrium. Now you see N has become very small and this is M. So this is the melt which is there. So now you can see M divided by M plus N, and N is becoming smaller. As it becoming smaller, the fraction of melt is coming close to 1. When will A get exhausted? When will A get exhausted? It is where this point will reach this point. So here it's L6 and here it's F6. Here you see the N now has become equal to 0. So this will be M divided by M and this will be 1. That means it's a fraction of melt is 1, means the last crystal of A. The last crystal of A has now been melted, or the rock has been entirely melted. So you can see here that when you have a rock having composed of minerals, at least for this binary system, let's say, when both A and B are there, the liquid composition cannot remain outside the eutectic. It has to be on the eutectic. So long A and B are there. So that is why you have L1, L2, L3 all plotting at the eutectic. You can't show it. But S1, S2, S3, the rock becomes more A-rich. Why? Because you're melting A50, B50, and the rock is A60, B40. So at the end of it, you will have A. At this point, the rock will not have any B. It will only have, the system will only have A plus liquid. And A plus liquid, this equilibrium works only along this line. So now the melt has to move away from the eutectic. And the temperatures, and now that's an interesting point. So the melt, the temperature now starts to increase as you're heating it. And you can see N becomes thinner and thinner and thinner and thinner till it becomes zero. When it becomes zero at X6, the last crystal of A has been exhausted out of the system. The last crystal of A has been exhausted out of the system. Now there is a very important corollary to this diagram. Now, while I say this for the binary system, it's also true for all other systems, ternary systems and everything. See, let us look at the beginning of the melting part. Beginning of the melting part, where you're heating the rock and it's going into melt. See what's happening. Again, from L1, L2, L3 to S1, S2, S3. Just concentrate in this part. See what is happening. You're supplying heat to the rock. But from L1 to L3, the temperature of the rock is not rising. It's the same. The rock, the system, does not change its temperature. As more and more melt is produced of eutectic composition, so long A and B is there, the temperature of the system does not change, does not increase. This means that when you melt a rock, the rock buffers temperature rise. So it is like a heat sink. It does not allow the temperature to rise. The more you heat, so long A and B are there, more melt is produced, higher productivity of melt. But the temperature does not rise. That is very critical. Only when that assemblage of minerals A and B, there is a change in that. Here, A goes out. B goes out. Then the temperature of melt starts to increase. Only then the temperature starts to increase. So long you have an assemblage working like here in the binary, the more heat you give, the more it goes, melt productivity increases, the volume fraction of the melt increases, but does not allow the temperature of a particular rock that is undergoing melting to rise. It just does not allow it. Have you understood? But also there is another catch. There is another catch. You see, after this, say S3 to S6, S3 to S6, what we are saying, that the temperature is rising. Yes, now the rock is no more buffering the temperature. The more you heat, the more melt is being produced, but the temperature is now not controlled by the system anymore. The system loses control of it. So now if you supply heat to the system, the temperature does not get buffered anymore and the temperature keeps on increasing. As you melt more and more of A till you reach L6, and thereafter you can heat it and the melt just melts. And the temperature, the melt simply gets down. So that's an important thing. So you can now see an important aspect of this phase petrological diagram, a fallout of this diagram. In this part, L1, L2, L3 to S1, S2, S3, at low degrees of melting. Low degree of melting means low volume fraction of melt. low volume fraction. These are high volume fraction when you produce more melts. But when you are melting at a low, small angles, at small amounts of melts are being produced, the temperature of the rock does not rise anymore. It won't rise. All the heat is taken up into latent heat of melting. And you produce higher and higher amounts of melts. But it does not make you rise to high temperatures. So when rocks melt at low degrees, the temperature of melting does not change very much. It cannot change. It will only once one of the minerals is exhausted out of the system. Only then will it change. Tell me, have you understood it? Now, it's very important that you realize what I'm talking about, and that's very important. There is nothing to mug up here. Not a single thing to mug up. You have to understand. That's it. If you understand phase diagram, there is nothing to mug up in the phase diagram. Nothing at all. You have only to understand phase diagrams. And then you don't need any more reading once you have understood the logic. Always understanding phase diagram, one good way is, say for example, think, oh, if I do this, this will happen. You just ask, you stop and ask yourself, why? Ask why. And you will stop in your tracks. And the good way of understanding phase diagram is, don't use pronouns. Don't say it. No. Discourage yourself from using the word it, that. If you want to say melt, say crystal, say proportion, say composition. Be specific. Don't use nouns. Use nouns. Do not use pronouns. When you say it means anything. When I say it qualifies all of the nouns that have come before it. It means nothing. That means nothing. You have to ask yourself questions based on on nouns. That this composition of what? Composition of solid, composition of melt, composition of what? Ask yourself question, why, what? And you see, you have to answer the question yourself. Now, this is not a physical class where I can ask students to come over and answer my question. Then it's much better. Understanding phase diagram is no small thing. It's quite big. Okay, so just quickly, one more small shot at this melting curve, equilibrium melting, so that possibly you get a little bit more efficient with the system. Okay. Again, I'm talking of equilibrium melting. So below this rock, from here to here, rock plus melt. Above this, melt. Now just quickly, let's say this is the eutectic composition. Let's say this is the eutectic composition, and this is my R0, and let's say I write this as A and this is B. So R0 is A40 and B60, let's say. A is A40, B60. Now, if I have a rock whose composition is this, what will happen? If I have a rock composed of minerals, pure minerals A, B, in the proportion 40 is to 60. In the proportion, weight proportion, 40 is to 60. So if I take this rock and melt it, what will happen? That's the question. So you take the rock and you heat it. The rock will melt at temperature TE at the eutectic temperature. The rock will melt at the eutectic temperature, and if the rock of course reaches this point, and when you have this rock with A40, B60 minerals in this weight ratio, what happens? The rock undergoes melting to produce a melt of what composition? Of the composition of the eutectic. That will have a composition A40, B60. The melt will also have the composition A40, B60. So you will have pure A, pure B, impure melt. This will be the situation where the impure melt will have the composition A40, B60. This will be the composition of this impure melt. And pure A and pure B will be in the proportion A40 and B60. So A and B in the pure, in the proportion 40 is to 60, will melt to give you a melt where A and B components are present in the ratio 40 is to 60 to make a chemically homogeneous melt. Have you understood? A chemically homogeneous melt. This will go on. Remember, you're at the eutectic, so the melt composition will not be able to change. Only thing, A and B, the proportion will change, and the proportion of A and B will also not change in the rock because they will be melting in the same proportion A and B is there, and you will produce a melt with this proportion A40, B60. Only thing, the proportion of melt or the melt fraction will increase, but the liquid will not change its composition. The liquid will not change its composition. So here is another important thing. You see, in this type of eutectic melting, the composition of the melt and the temperature of melting does not change. Both do not change. Neither the composition of the melt changes, nor the temperature of the melt changes, all through its range of melting. Because the minerals are in the proportion of the eutectic. Have you understood? Okay, in the next class we go into solid solution. I think you have been able to learn a bit new things, and I will tell you more about it. But next class we'll talk of solid solution. Remember, we had taken XA solid equal to 1, XB solid equal to 1. So we took pure solids. Now in the next class we will go into impure solids. Thank you.